outline will 4 point the general balance equation, natural balance, energy balance on single phase non-reactive processes, and simultaneous and transient balance. A system is to be in transient or unsteady state condition if the value of any system variable changes with time. Batch and semi-batch process systems are always transient. In a batch system, if nothing is changing with time, then nothing is happening. And in a semi-batch system which has an input stream but no output stream, or vice versa, at least the mass of the system content must vary with time. Continuous systems are always transient when they are started up and shut down, and they become transient at other times due to planned or unexpected changes in operating conditions. The procedure for deriving balances on transient systems are essentially those developed in material balance and energy balance. The main difference is that transient balance have non-zero accumulation terms that are derivative. So that instead of algebraic equation, the balance are differential equation. In reality, the concept of a true steady state is fiction, since there are always process variable fluctuation in real system. When you assume the state operation, you are assuming that these fluctuations are small enough to be neglected, which causing serious error in calculated value. The general balance equation. The general balance equation was given as accumulation equal to input plus generation minus output minus consumption. Two forms of this equation were discussed: differential balance, which relate instantaneous rate of change at a moment in time, and integral balance, which relate changes that occur over an infinite time period. We examine in this section the nature of the relationship between these two types of balances. In doing so, we belatedly show why they are called differential and integral. Differential balance. Let's m in kg per second and m of kg per second be the rate at which species A enters and leaves the process by crossing the boundaries, and let R generation kg per second and R consumption be the rate of generation and consumption of A within the system by chemical reaction. Any or all of the variable m in, m out, origin and archon may vary with time. Let us now write a balance on A for a period of time from t to t plus delta t. Supposing that delta t is small enough for the quantity m in, m out, origin and archons to be considered constant. The term of a balance on A are usually calculated. Input equal to m in times delta t, output equal to m out delta t, generation is R gen delta t, consumption is R con delta t. We also suppose that the mass of A in the system changes by an amount delta m during this small time interval. By definition, delta m is the accumulation of A in the system. From the balance equation, delta m equal to m in plus R gen minus m out minus R cons delta t. If now we divide by delta t and then let's have delta t approaches 0, the ratio delta m over delta t becomes the derivative of m with respect to t, dm over dt, and the balance equation becomes dm over dt equals to m in plus r gen minus m out minus r cos. This is the general differential balance equation. M is the amount of valence quantity in the system, and the four terms on the right side are red that may vary with time. If equation 10.1-2 is applied to a continuous system at steady state, the quantity M must be a constant, its time derivative therefore equals 0, and the equation reduced to input plus generation equal to output plus consumption. However, as long as any term varies with time derivation, the derivative on the left side of the equation 10.1 is 2 remain part of the equation. It is concluded that the balance equation for an unsteady state system at an instant of time is the differential equation, hence the term differential balance. The procedure for deriving a differential balance on an unsteady state system normally begins with three steps. First, delete terms from the general balance equation that are either 0 or negligible. Second, write an expression for the total amount of the balance quantity, mass, particle, mole of species, energy in the system. Step 3, differentiate the expression with respect to time to determine the accumulation term. Thereafter, substitute expression for the non-zero term in the equation, cancel variable if possible, and formulate a boundary condition or an initial condition at t equal to 0. Example. A continuous two-tank reactor is used to produce a compound R in a liquid phase reaction A equal to R. It enters the reactor at a rate of V naught liter per second. The concentration of the reactant in the feed is CaO, mole A per liter, and the volume of the tank content is V per liter. The vessel may be considered perfectly mixed so that the concentration of A in the equal stream in the product stream equal that in the tank. For this process, the rate of consumption of A equal kCa mole per second liter of reaction volume. All fluid, the feed, the tank content, and the product may be taken to have the same density, raw gram per liter. Write differential expressing the balance term of the variable shown on the following diagram. To solve this question, first, given total mass balance generation equal to 0, consumption equal to 0, accumulation equal to input minus output, mass in vector m gram, mass m in gram equal to V time rho density. Therefore, accumulation gram per second is equal to dm over dt equal to dv times density over dt equal to rho dv over dt, since rho is a constant. Input gram per second equal to v naught times rho. Output is v dot times rho density Therefore, rho dv over dt equal to v naught rho minus v rho. Can cancel rho. Therefore, dv over dt equal to v naught minus v. At t equal to 0, v is equal to v naught, where v naught is the initial volume of the tank contents. Balance on A accumulation equal to input minus output minus consumption. Mole of A in the reactor equal to V times CA. Accumulation mole A per second equal to dVCA over dt. Input equal to V naught times CAO. COO is the content of A in the initial tank content. Output is V times CA. Consumption is KCA. Therefore, the equation is dVCA over dt equal to V naught CA naught minus VCA minus KCV, because we have a consumption here. So at t equal to 0, CA equal to CA naught. The procedure to follow when solving a problem involving a transient balance is to derive the differential balance equation, integrate it between initial and final time, and solve for the desired quantity or function of time. Thank you.